Testing, 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 testing. All right. Looks like we're live. Welcome to another HoopPo stream. Today we got a paper to read through. This is a paper coming out of Amazon Web Services, so AWS, of course, everyone's favorite cloud computing service. Hey bro, you are 10 minutes late. I'm sorry. I don't have like a specific routine. I kind of just wake up and make coffee and I get here. I'm sorry about that. The Max Planck Institute is also a very good university, so kind of a combination of Amazon and Max Planck. I did not realize that Amazon had a office in Germany, but I guess they do. 20th of April 2023, so relatively recent. No, you're good. Yeah, so I actually did work for Amazon a very long time ago, but I worked for this company, Kiva Systems, which was acquired by Amazon and does all the robotics, and I did simulations and kind of layout optimizations, but it's been a long time since I've worked at Amazon. So this paper, I picked it because it was very interesting to me, but basically they're doing augmentation, right? Data augmentation, so if you guys are familiar with that, things like left-right flipping, horizontal, adding Gaussian noise. There's a variety of different augmentations. It's a variety of different data set augmentation libraries. This one's a very popular one, for example. You'll take an image, you can shift it, you can change it, but fundamentally the semantic meaning of the image is the same, it's maintained. So it's a way to take one image in your data set and turn it into potentially hundreds of different images. And it artificially increases the size of your data set, and then you can benefit from kind of the power laws and the scaling laws that bigger data sets results in better performance. So data augmentation is a very important part of any machine learning project, and pretty much every single type of machine learning algorithm you can think of, someone has tried to make sure that data augmentation is part of that, right? So even in text data, I've seen augmentation strategies. But one thing I haven't seen before is the use of diffusion models to generate data augmentations. So I thought this was a very interesting idea, and I kind of figured let's check it out and see if there's something to it. So unfortunately for us, there's not really any good pictures in this. This looks like right off the first page, they kind of show you there's no images here, which isn't great because then people don't get attracted to the paper and then nobody ends up reading the paper. So we're going to kind of scroll and see what we find here in one of these figures, and then maybe we have a better idea of what's going on here. So we generate images by guiding the stable diffusion model. So already they're telling us that the diffusion model they're using is a stable diffusion one, by text prompts or learned conditioning. Okay, prompt or learned conditioning. We don't know what learned conditioning means yet. So maybe some class, right? Like a category, like an ImageNet category or something. Retrieving images by a nearest neighbor search. So nearest neighbor search is just a simple algorithm to find or to cluster points of data based on their distance in some space, right? So you can do nearest neighbor. In this case, they're doing it in the clip embedding space, right? So things that are similar in the clip embedding space are going to be clustered. Things that are different further apart in the clip embedding space are not going to be semantically similar. We then train the downstream classifier on the original 10% ImageNet data augmented by the additional data and evaluate on the original ImageNet validation split. Okay. So you see they have pictures of parrots here. They take that. I don't know what this step is, but somehow diffusion model or dataset retrieval, they use the clip embedding to find similar-ish images and then add those images at train time. So I'm curious whether they'll be kind of doing this per batch or whether they do it at the very beginning for the entire data set. Like, is this more of a kind of in the loop augmentation, like at runtime augmentation, or is this an augmentation that you would do beforehand and kind of an offline thing and then you would train as you would normally? So lots of questions. I think we hopefully will have them answered, and let's get to it. We got abstract. Diffusion models, not a new idea. I guess it already had been done with GANs. Yeah, I've seen data augmentation with GANs before, but I've never seen it with diffusion models. Diffusion models excel at generating photorealistic images from text queries. Naturally, many approaches have been proposed to use these generative abilities to augment training datasets for downstream tasks such as classification. Yeah, so maybe there is a bunch of work. Maybe there's like a whole like research area where they use diffusion models for data augmentation. Diffusion models are themselves trained on large, noisy, supervised, but nonetheless annotated datasets. It is an open question whether the generalization capability of diffusion models beyond using the additional data of the pre-training process for augmentation leads to improved performance. We perform a systematic evaluation of existing methods to generate images from diffusion models and study new extensions to assess their benefit for data augmentation. We find that personalizing diffusion models towards the target data outperforms simple prompting strategies. Okay, so we don't know what personalizing means, right? That's not common jargon there. They're going to define that, whatever that means. We also show that using the training data of the diffusion model alone via a simple nearest neighbor retrieval procedure, so this is how they're going to find the related images in the dataset, leads to an even stronger downstream performance. Our study probes the limitations of diffusion models for data augmentation, but also highlights its potential in generating new training data to improve performance. Yeah, this is the more interesting part. So I would say data augmentation right now is somewhat limited to the idea of taking data that already exists and then modifying it slightly in order to make sure that the semantic meaning of that individual data point is maintained. But now that we have generative image models, right, why not just generate an entirely new image and then use that to train on, right? And you don't have the guarantee that the semantic meaning in that generated image is exactly what you want to be training on, but I feel like image generation models are pretty good nowadays. And if you ask Stable Diffusion to give you a picture of a dog, you can probably trust that that's enough dog to train a classifier. I don't know why you would necessarily want to train a classifier, but yeah, then it becomes kind of this distribution thing of like, what is the point of generating data if the data already exists in the clip embedding space? That's the intuition I get. Yeah, it's kind of, I don't know, it's difficult to say, right? Because it's kind of like, what's the point of training a segmentation model if you already have a foundational segmentation model like segment anything, right? The only reason you would train a new segmentation model is if your data is so out of distribution, right? Maybe it's like X-ray images. It's so out of distribution that you can't just use the foundation model like segment anything out of the box. But if you can't just use the segmentation or the foundation model out of the box, then you're not going to be able to generate X-ray images with Stable Diffusion, right? So it's kind of like I don't know exactly the situation where you would want to do it. But this paper doesn't necessarily propose that, right? In this abstract, to me, this reads like a kind of like a science experiment paper, right? Where they're like, hey, we are curious about this particular technique, let's try it out, let's try a bunch of different ways of doing it and see how it affects it. So this isn't a paper that's saying, hey, we have this new technique and it's going to result in new state-of-the-art results. This is almost more of an understanding, kind of like trying to look at the black box paper, right, where you're like, hey, here's some weird thing, we're going to look at it on MNIST and CFAR, and we're going to try a couple different things, and the point is not to create a new novel technique. The point is to basically explore how it affects the training so that we can better understand what training means, what data augmentation means, and so on. And that's kind of the kind of papers that I feel like you can really learn from, right? Papers where they're more experimenting and they're not necessarily just saying, here's some shiny new thing that gets us state-of-the-art, but we have no idea why it gives us state-of-the-art. Yeah, that's another good point, is that the diffusion model is the data set, right? The diffusion model is a compressed representation of your data set distribution. But that's the fundamental problem, right? Is that it's a compressed representation of the data set distribution that you probably already have in your pre-trained encoder, right? So you're probably not starting from scratch. You're probably using a pre-trained model, and I bet you that pre-trained model in Stable Diffusion, those data set distributions are basically right on top of each other. Data augmentation is a key component of training robust and high-performing computer vision models, and given its success, it's become increasingly sophisticated. From the early simple image transformations, cropping, flipping, coloring, color jittering, and shearing, so that's the ones that kind of most people have used, to more complicated ones such as mix-up and cut mix. These are, I don't think they're in Augmentations. Yeah, they're not here, but there's another library called ImageAug. Yeah, this one. I've used this one before too. This is the more complicated one. So like cut mix. I don't know if they have a cut mix here. No, they don't have a good example of cut mix. But cut mix is basically the same thing. It's like you're cutting parts. You're playing like Adobe Photoshop with your images in an automated way. Augmentation, image augmentation using generative models. So here you go. This is what you were referring to, Kalina. People have done image augmentation with GANs. Image transformation makes it more robust. Interpolating augmentations are particularly helpful where diverse training data is scarce. With the success of GANs, generative models finally scaled to high-dimensional domains and allowed the generation of photorealistic images. I don't know if I would call the early GANs photorealistic, but they certainly were images. The ideas of using them for data augmentation purposes has been prevalent since their early success and forms the basis of a new set of data augmentation strategies. Okay, so you do have here a whole bunch of references for data augmentation that are based on image generation. Given the emergence of diffusion models that outperform GANs, even this is not necessarily confirmed, right? I think we've read papers that go back and forth on this. I remember we read a paper that said diffusion models beat GANs, and then we read another paper that was, no, GANs are still better than diffusion models, and then we read another paper that's diffusion models are better than the GANs. So like, it seems like there's still this kind of constant war between model architectures, right? The same way that convnets and transformers, right? You have convnext, which was trying to say that, okay, convnets are still there, transformers haven't taken over, and then transformers take over. So like, you're kind of seeing these like architecture wars where people basically stick to a specific architecture and then try to beat the opposing one, and they keep getting higher. So maybe the underlying truth there that neither of them wants to admit is that the model architecture doesn't matter, and that really it's dataset scale and training time, and those are the only reasons that these models get better over time, not the model architecture. Unlike GANs, diffusion models can be easily conditioned using text queries. You can query a GAN with a text. Have people done that yet? Conditioned GANs on text? I don't think there's anything which would prevent you from doing that, right? which allow for more controlled data generation. These models are trained on a large data set of billions of filtered image text pairs retrieved from the internet, enabling them to generate images of unparalleled variety. We benchmark a variety of existing augmentation techniques based on diffusion models and propose new extensions and variants. Simple text prompts based on class labels suffice for conditioning the DM to improve the performance of standard classifiers. Okay, so maybe this isn't something you would use to improve or to create a new classification model from scratch, but maybe it's something you could use to almost like further fine-tune your model such that it performs even better on your problem. Okay, so this hints at an actual real-world use case for this, where, hey, you already have a classifier that maybe you're using for an autonomous vehicle, and it's sitting at 99.9% performance, and you've tried everything, you can't figure out how to get an extra 9 of performance there, but because you're in autonomous vehicles, you really need to squeeze out that extra 9, right? So maybe the way that you would use this is you would basically use the diffusion model to generate samples, generate images that are right on the boundary between two different classes, right? So kind of the famous panda gibbon image, right? Panda gibbon, everyone's seen this one, but basically you have this image of a panda, you add what appears to be a noise, and then it turns into a very high confidence for gibbon, right? And what they're really telling you here is that Wolfram Alpha LLMs or something like that. I remember this. Yeah, this image here. So at the end of the day, what a neural net is doing is it's creating a basically these boundaries in an embedding space, right? So here, this red might represent panda, and this blue might represent gibbon. So this image of a panda is right on the edge. It's right on the edge here of what is considered a panda. And if you add just a little bit of noise, and that noise is in the direction of the blue, now it's going to suddenly turn it into gibbon. So that is the reason you have these kind of adversarial examples, is because the adversarial examples are basically right on the boundaries of the separated space that the neural net creates. So perhaps this type of data augmentation using diffusion models could be a way of sampling images that are very close to that boundary, right? And then training on those, and thus making these boundaries better and better over time, and thus making your model more robust. So that's a real-world use case that could come from this. As images generated by simple prompts match the training distribution of the diffusion model and not the training distribution of the classifiers. Yeah, so I would say that these are a little bit closer than they say they are. The training distribution of the classifiers are probably going to be very similar to the training distribution of the diffusion model because everything is ImageNet. And optionally, the DM's denoising model component. The fine-tuned models outperform the best performing strategies, the best prompting strategies for their ability to create even better synthetic data for augmentation. I've also done some synthetic data stuff, BTW. Surprisingly, we find that simply retrieving nearest neighbors from the DM's training dataset using the same clip-like model used in the diffusion model with simple prompts is a very strong augmentation strategy. I like this paper out there. They're not afraid to use strong words. Right, look at this, unparalleled variety. Very strong augmentation strategy. You don't usually see very like kind of opinionated language like that. So it's interesting that this paper has very opinionated language. This strategy outperforms all investigated methods based on generating synthetic images, suggesting that the true potential of diffusion models for data augmentation is not yet fully realized. Okay, so they themselves are saying, hey, this could be even bigger, and that there is a large opportunity. Okay, the wording here is so aggressive that I'm going to start taking it with a little grain of salt. You know, they're so excited about it that I'm like, okay, it's probably not that good. All right. Are generative models beneficial for data augmentation? We got here a little figure 1. We seem to have classifier top 1 accuracy, so Top 1 accuracy is basically a classifier's ability to guess the correct class perfectly, right? So in ImageNet, you have maybe 1,000 different categories, such as chair, couch, car, dog, cat. You give a classification model image, it gives you a probability distribution over every single basically class, and then you pick the one that has the highest confidence, the highest probability of being that class. And in top 1 accuracy, that needs to be perfect. So if it's an image of a dog, you better say dog instead of wolf, right? So here they're saying if you train on 10% of ImageNet, you only get roughly 57% top 1 accuracy. And then here are their kind of approaches here. So they have 3 different things they did here: DM prompt based, DM fine tune, and then retrieval, which is the K nearest neighbors search they were describing probably. And you can see here how the retrieval one actually works the best. And this little bar right here, this little line is the error bar. So they probably did this with a bunch of different random seeds, a couple different runs for each one. And the lowest one they got was here, and the highest one they got was here. So that's a bar chart with error bars. Each bar shows the accuracy along with a standard error for the downstream classifier based on the best augmentation methods within each family. What does this mean? Okay, within each family. So each of these, they're calling them families of augmentation methods. A simple retrieval method using images from the diffusion model's pre-training dataset directly performs best. This suggests that the generative capabilities of diffusion models for augmentation have not yet fully been leveraged. Alright, let's look at some related work here. This is a very short related work section. It's barely even a page, so data augmentation using generative adversarial networks. Data augmentation is widely used when training deep networks. Okay. It overcomes some challenges associated with training on small data sets and improving the generalization of the trained models. Manually designed augmentation methods have limited flexibility, and using ML-generated data for training has attracted attention. So here you go in, let's see how old these papers are actually. So 2020, you had a GAN paper for generating data. Let's see what else we got. Despite early promising results, the use of GANs to generate synthetic training data has shown limited advantages over traditional data augmentation methods. Yeah, that's my kind of insight on this too. So when I had a synthetic data startup, we tried to do this. We tried to use GANs to generate synthetic data, and it just wasn't worth it, because you had to train the GAN on the data distribution that you were interested in, and then that took a bunch of time and money and effort, and then you generated each of the images, which you then had to filter because you had no way of getting the label for that image. So it just felt like a lot of work for not enough performance gain. So that was probably 5 years ago at this point, so obviously technology has improved, but yeah, my intuition is that GANs for synthetic data are just not good enough, but they could be good enough now. Diffusion models could be a better candidate. Yeah, there will be, right? You could almost think of Stable Diffusion as a foundational generative model, right? Or GPT, right? GPT is a generative pre-trained transformer, so it's kind of like you fine-tune in a small data set and it can generate lots of data. Yeah, I think that'll exist. I think you could use image. I'm just, so right now in terms of foundational models, I think the best foundational model for text is obviously GPT. The best foundational model for images, I think, is the Dino V2 that Facebook released. But the best foundational model for both images and text right now is just Clip, right? And then maybe Blip 2. But Clip and Blip 2 are like not that great anymore. I feel like there's an opportunity to make a really, really good foundational model that is not just, that is images and text, like the Clip successors. Like someone needs to make a much better Clip. because I feel like the multimodality of images and text is just so strong. There's so much potential information there that we really need someone to make a clip v2 or like a clip v3 and so on. Diffusion models, okay, whatever. In this work, we focus on diffusion models. Cool, cool. Let's see what else they got. Data augmentation using diffusion models. So here they have a bunch of diffusion model papers. Numerous approaches have been published that adapt diffusion models to better fit new images and can be used for augmentation. Sneeze mode. Astonishing results. Yeah. These guys are, maybe it's like German, so all these people are German, obviously. Berg, Florian, Dominic, Zietlow. So maybe like German people, just the way, I don't actually speak any German, so like maybe the way that you speak in Germany, you use a lot of adjectives, a lot of strong kind of opinionated language, so maybe that's kind of what's coming through here. Like that's one thing that I noticed too, right? Is that papers that come out of, for example, like Chinese universities tend to be very like tame, very like, here's the thing, very dry, mathematical, and then maybe papers that come out of Germany are a little bit more passionate, a little bit more strongly worded. But I'm just generalizing. We evaluate methods that employ diffusion models in a guidance-free manner. So guidance-free manner basically means that you don't have a text embedding that you're using as a condition when you generate, right? The text embedding is called the guidance vector a lot of times. Generate variations of a data set by first adding noise to the image. Yeah, so this is another way you could do it. Rather than generating new images, you could basically just use the noise part of the diffusion model to add noise and then remove the noise, and then in that way you get an image that's basically the same but just like slightly different, right? So in a diffusion model you're progressively adding noise step by step, so basically all you would do is just add noise for one step and remove noise in one step. Yeah, that's clever, I like that, right? And generate a synthetic ImageNet clone using only the class names. We also evaluate methods for specializing, aka personalizing. So here they define the personalizing word. They mentioned this word, personalizing, but I was like, that's not an actual real word. What the fuck do they mean by that? And what they do mean by that is specialization, so basically task specific. Given a few images of the same object or concept, we learn a joint word embedding. Oh, that's pretty cool. These are pretty fucking, these are little cool little ideas here. So basically, I have a bunch of images that potentially my classifier isn't working well on. I feed all of those images into clip, right? Clip gives me a word vector for all of those, and then I somehow take the average of all those word vectors, and that new word is going to represent basically a pseudo word, like some kind of word embedding that represents the exact type of image that your model is not good at. So that's kind of a cool cool little trick there, right? Use the word embedding space as a kind of proxy for like the semantic concept that you are not performing well on. Recently extended their methods to significantly reduce the number of required training steps. Follow a similar approach and proposes a method for text conditioned image editing by fine-tuning and learning a new word embedding that aligns the input image and the target text. We investigate the usefulness of this personalization or specialization for data augmentation, which was not conclusively addressed. Propose and evaluate extensions of these methods tailored to data augmentation and provide thorough evaluation. Yeah, this is what I want to see. This is why I'm reading this paper. I want to see what the experiments are. Show me what is actually happening. There have been multiple concurrently proposed methods that we could not include in our study. Alternative losses for image generation, optimizing the features of the embedded images, or using alternative prompts. Other methods focus on fine-tuning the diffusion model, learning a unique identifier for the given subject, utilizing image synthesis, in-painting, blah, blah, blah. We augment using a wide range of generative and retrieval-based techniques and evaluate the performance. Okay, so we sample 10% of ImageNet large-scale visualization. Okay, and this is the full name of ImageNet if you were ever curious. It's ImageNet Large Scale Visual Recognition Challenge 2012, ILSVRC 2012. But don't actually ever use this full name because that's unnecessary. Just call it ImageNet. Training split, retaining class imbalance. So what they're referring to here is that ImageNet is not balanced, as in there's a lot more pictures of dogs than there are of, I don't know, maybe trash cans or something like that. Like there's an imbalance in the classes, and they sampled 10% of ImageNet. They want a small version of ImageNet, but they want to make sure that it still has that imbalance in the classes, right? They were excluded, so some of the ImageNet classes, there's 1,000 total, right? That's the ImageNet 1K. The 1K stands for 1,000 different classes. They're saying that some of them had such a low amount of examples that they basically just removed them. We sample a disjoint set of images from the same size from the training split for hyperparameter optimization and model selection, which we refer to as a validation set split. So disjoint set here just means basically separated, right? You don't want to be training on your validation data. You don't want to be testing on your training data. So you want to keep your train, your validate, and your testing, all three of those data distributions should be separate. There should be no overlap. So they're making sure to dot their I's and cross their T's. Okay, for each augmentation strategy, we generate 390 samples per class, ensuring that the number of images is at least tripled per class. Okay, so basically they 3 times the amount of data with the augmentation. We resample the additional data into 5 sets containing the same number of samples per class as our ImageNet subset and train a ResNet 50 classifier. This is a pretty ancient model architecture here. During training, the samples, the reason they pick this, also by the way, it's like they're not picking a ResNet 50 classifier because it's the best classifier. They're picking a ResNet 50 classifier because it's very fast to train, right? A ResNet 50 you can train significantly faster than a ResNet 101, right? ResNet 50 only has 50 layers, ResNet 101 has 100 layers, twice as deep. So what they really want to do is compare, right, these different augmentation strategies. So they're not looking to get a state-of-the-art result. They're not trying to pick the biggest, baddest model they can. They're trying to purposefully pick a very small model that they can use for experimental purposes, right? During training, the samples are further augmented by random resizing and cropping. Okay, so they also do random resize and cropping. Batch size of 256. That's quite a big batch size. So they're definitely using big GPUs. Learning rate of 0.1, which is actually quite big. That's a big learning rate. Then they have here a learning rate scheduling. So they're doing learning rate scheduling that's conditional on the validation accuracy. We stopped training when the validation accuracy did not improve for 20 epochs or after at most 270 epochs. Each model was trained on 8 NVIDIA T4 GPUs using distributed data parallel training. Okay, so there you go. That's how. See, this batch size of 256, that's an extremely big batch size, right? You're not going to fit that on a single GPU. So as soon as you see a batch size like that, you know they're doing distributed training, right? So they're doing distributed training on 8 NVIDIA T4s, which means that there's 8 NVIDIA T4s, and it's distributed data training, which means that the same model, the same little ResNet 50, is on each of the 8 T4 GPUs. And then each of those 8 T4 GPUs that has the same ResNet 50 on it is getting 1/8 of the 256 batch size. So if you do 1/8 times 256, 32. So each of these GPUs is getting a batch of 32. Augmentation methods. The benchmarked augmentation methods can be grouped into 4 categories. So these are the 4 categories. Guidance-free diffusion model sampling. So guidance-free just means they're not using a text embedding to condition the generation. Simple conditioning techniques with which prompts based on the object's class label. So here they are using a conditioning or a guidance vector, and it's just the class label. So dog, washing machine, car, whatever it is. Personalization techniques that fine-tune the diffusion model conditioning and optionally the diffusion model itself. Okay, so that's some kind of fancy fine-tuning. And then a baseline. So the last one is basically just images retrieved from the data set that the diffusion model was trained on. Okay, so this is interesting. It's not the data set that they want to train on, it's the data set that the diffusion model was trained on. Following the procedure of 0, boomerang, what the fuck is this? I've never seen that before. It's almost like a, that's kind of interesting. It's like numbers, right? So like they refer to specific parts of the figure. That's kind of cool. So when you're reading a machine learning paper, right, whenever you see these bracket numbers, this is a paper. This is a reference to another paper, right? So 14 just means you go here and you look at number 14 and it's this. So here's the actual full paper that they're referring to. And people will also reference figures. So if like they're like, hey, look at figure 2 or section 4.2, right? And they'll say section 4.2. So you can go, results is section 4, section 4.2 is this. But this is something interesting that I haven't seen before, right? Where they basically say, this within this figure, there's like little sections. So this is section 0 of the figure, section 1, section 2, section whatever, 3, 4. And then here they're referring to section 0 of the figure. So I haven't seen that before. That's pretty cool. We investigated a guidance-free method that does not require conditioning or updating the diffusion. Instead, the approach adds noise to individual samples before denoising them. Hello, Uzi. So, okay. In this technique, you start from your ImageNet 10%, which is just the small version of ImageNet that they created. You add a step of noise, you remove the step of noise, and then those should largely be the same. And I guess the reconstruction objective here is training the diffusion model itself. We reference each method by a circled number. Some methods edit the prompt while keeping the diffusion model frozen. Another family of methods optimize the conditioning vectors for the given images and then jointly fine-tunes the DM. So there's a lot of different techniques here, right? So the diffusion model, they're either going to keep it frozen or not frozen. Frozen means that they're not pushing gradients into it, right? Not frozen means that they are pushing gradients into it. They are kind of improving it over time, making it more task-specific. Can you share Oculus branch for Unreal file? I really need mixed reality simple. So, I mean, you can just go on GitHub, Unreal Engine, Oculus. Right here. So this is the Oculus Unreal Engine, and then within here you want to go to the release for the Unreal Engine version that you want. I haven't done any like VR stuff in like months though, so I have no idea if this is still even alive. It looks like they're still pushing. Should probably use this one. Go to this. Hope that helps, Ulzi. Okay, what were we doing? We were talking about the diffusion model, and basically either they're changing the conditioning vectors, or they're changing the diffusion model. Here you have the pseudo word representation, where you can take your images, get the text encoded version of them, get the word vector associated with that image, and then that pseudo word gets added to the actual name. So this is the whenever they have the class name, this is the text that they actually turn into an embedding. So they don't just turn the word dog into an embedding, they would say a photo of a dog, and then they feed that and turn it into a text embedding. We explore several prompt-based methods of guiding the diffusion model to produce samples for a specific class. We condition the model by simple prompts containing the object's class name, prompting the diffusion model with a photo of n and a version of it. Yeah, so this is just the object name and then a photo of the object name. Stripping white space. Look at that, they have a function definition for white space stripping. It seems a little bit unnecessary. A photo of many WN, a black and white photo of WN. That's kind of cool. So what does the dot mean? This dot here, I think it's literally a period. So this is just a prompt, right? They're prompt engineering something here. So basically, rather than just say dog, it would be a photo of dog with the white spaces removed, period. This dot here, it just means whatever that is. It means you can put anything in there. So W is not a function of any specific variable, it's just a function of anything, where you could just replace dot with N or X or F or whatever you want. Hope that answers your question, RW. A set of templates proposed to create a blah, blah. Okay. We explore various methods for fine-tuning a DM for class-personalized sampling to improve reconstruction of the classification dataset. Class-personalized sampling. Okay. FT conditioning, freezing the diffusion model and optimizing one conditioning per class. FT cluster conditioning, optimizing multiple conditionings per class instead of just one. So conditionings here are going to be actual word vectors, or not word vectors, but like the phrase, right? Inspired by Imagic, jointly fine-tuning the conditioning and the DM's denoising component. Yeah, so they're fine-tuning both of the parts. I've never seen a dot used as a variable name. Yeah, I think that's the whole point, is that this function here, which they're calling the white space stripping, right, which is literally just like removing the white space, is not a function of a specific variable. It's just a function of whatever you want to put in there. So it's just kind of a way of saying this is a function that takes anything. As a baseline comparison, we use Retrieval to select images from the Layon dataset. So this is a different dataset. This is the one that's used to train the diffusion model. It's not ImageNet, but similar. Method finds nearest neighbor images to the simple prompt, class name prompts in the clip embedding space. Yeah, so then they're basically doing a nearest neighbor in the clip embedding space in order to find similar images or similar class name prompts. We use the pre-trained Stable Diffusion v1.4 network, so this is the actual diffusion model they're using. Still the old one, you know, like, I feel like, what is Stable Diffusion at? I feel like they're at 2.0, right? Yeah, so they've released 2.1. models. They don't even tell you. API. Like, I just want to know where they're at this point. Text to image. So they have v2.2 here, so I guess that's probably the latest one. So these guys are still using a pretty old one here, v1.4. That's like the first one that they really released. Based on latent diffusion. So latent diffusion just means that you're performing diffusion in a latent space, which basically just means on the little latent vector, which is actually more like a 2D little square. We use the provided safety checker to discard generating images if marked as not safe for work, replacing them with new samples. Image sizes of 512 pixels, so that's just kind of, that's actually a little bit bigger than normal. I think ImageNet is smaller than that. For prompt-based sampling methods, we generated prompts based on the ImageNet class names defined by WordNet synth sets, representing distinct entities in the WordNet graph. Each synth set consists of one or multiple lemmas describing the class. The fuck is that? So lemma is like a concept from like math proofs, right? But what is a lemma in the context of prompt engineering? Good thing I have GPT-4 here. Let's see. Can I copy this? Isn't that from linguistics? Yeah. What is a lemma in the context of image dataset synsets? Oh God, come on. Come on, GPT-4. Synonym sets refers to a canonical form of a word or concept that represents a related word or concepts. Okay, so it's kind of like a hierarchy of kind of words that are related to each other. Yeah, so it's kind of like almost like a knowledge graph kind of thing. Lemma is a canonical form used to organize images based on their semantic content. So who is Galeocerdo Cuiberi? Galeocerdo is a shark. Okay, so this is, okay, that makes more sense. This is the Latin name for a shark, and this is basically saying if you have a class that has multiple names that refer to the same thing, we're going to have basically all of these words separated with commas. Providing multiple lemmas leads to better performance than only using the first lemma in the synset. Kind of makes a ton of sense, right? If there's lots of different words that all refer to the same semantic concept in your image, you're better off using all of the words rather than just one of the words. Sarilis provided multiple categories of prompt templates, class name only, class name with hypernyms, additionally combined with multiple different specifications, class name with definition, class name with a hypernym and randomly sampled backgrounds, blah, blah, blah. Here we sampled for each category the same number of images randomly across the background templates. Okay, so they have maybe some background templates. That sounds a little complicated because at that point maybe they're referring to background templates for the prompt. Yeah, so the background template of the prompt would be something like a photo of, and then you would put the the specific lemma of your thing, your category. So that's kind of interesting. I've never heard of the prompt engineering kind of boilerplate being referred to as a background template. But it totally is. That's totally what it is. It's a background template. So that's kind of an interesting little terminology there. I like that. For all methods that require additional fine-tuning, we train the model with the default stable diffusion optimization technique until the validation loss stagnated or increased. No model was trained for more than 40 epochs. Okay, 40 epochs. One epoch is basically one time through your training data set. So it's also important to note that they're using a small version of ImageNet, right? They're using the 10% ImageNet. So one epoch of a full ImageNet is going to be much more intense than one epoch of a 10% of ImageNet. We set hyperparameters in accordance with published works or existing code when available. Scaling to larger batch sizes was implemented by square root scaling the learning rate to ensure constant gradient variance. Boo's doing something in the background. We performed a fine-grained grid search for the optimal learning rate. So a grid search is a type of a hyperparameter sweep, right? So in most hyperparameter sweeping packages, random search and grid search are actually the easiest and honestly the one that people use the most. There's a couple other kind of like Bayesian-based searching algorithms, but grid search to find the optimal learning rate seems pretty standard. We clustered the training images within a class using k-means on the interception, so they're using the k closest neighbors. KNN, hello, human in the background. She's got the cat. There you go. She's making sure that Boo doesn't ruin the image. Inception v3 embedding. So that's actually kind of cool. They're using the Inception net embeddings to cluster the images. I thought they would have used the clip embeddings to cluster the images. For textual inversion, we fine-tune the text embedding vector corresponding to the introduce pseudo word n and sample from the provided text templates. Yeah, Inception v3 is from the age of dinosaurs. Why do people still use this stuff? I don't know. That's the real answer. Like, why don't you use clip, right? I think sometimes it's because they probably already have that available, right? They, in this research lab, right, they probably have a copy of ImageNet, and then that copy of ImageNet is in some kind of database that one of the columns is the Inception v3 embedding. So when you're sitting here in Amazon and you're working on this research project, you're like, okay, well, I have my ImageNet database and I have all the images that correspond, and I could create a script that goes through each image in my database and then loads a clip model and then runs it through the clip model, creates an embedding, and then writes that to a new column in the database and then do that for the entire ImageNet. Or it looks like someone already did that 5 years ago with Inception v3 model, so I'm just going to use their Inception v3 embeddings because it's probably just as good. So that's my guess, is that usually sometimes when people use these things, it's kind of coming from laziness and convenience, and it's not because it's like optimal, because using Inception v3 embeddings, as your intuition is telling you, Kalina, it's not optimal. You would be better off using a more rich and modern embedding space like clip, or even like the segment anything or the Dino v2 model. We initialized the pseudo word embedding in the final word in the first synset lemma. Where this initialization resulted in multiple initial tokens, we initialize with the mean of the embedding. So this is the average, and this is a little dicey, right? Is the average of the embeddings the same, right? Like if you take I don't know, like the word embedding for like a poodle, the word embedding for a chihuahua, and the word embedding for like a German shepherd. And those are all dogs, and those all have some point that they correspond to in the embedding space of the words. But if you take the average of those embeddings, if you take the mean of that embedding, does that interpolated point actually mean something? Does it have the same semantic meaning? I don't know for sure, right? I think that these embedding spaces are a little bit more complicated than that, and the average of embedding vectors isn't necessarily maintaining that semantic meaning, right? So I don't know. I think when you take a mean of embedding vectors, you might be going into a little bit of unknown territory. For each fine-tuning run, we store checkpoints with the best train and validation loss, and those corresponding to 1, 2, and 3 epochs of training. In the case of Imagic, we found that the validation loss was still decreasing after 40 epochs. So validation loss, you look at it to see how much you're overfitting, right? So everybody knows the overfitting curve, right? Where you have your losses, you have your training loss, and your training loss is always going to go down, but at some point it's basically overfitting, right? As soon as your validation starts going up, that means you're overfitting. But what they're saying here is that, hey, even after 40 epochs, the validation loss was still going down, which means we weren't overfitting. So we didn't stop it because we were overfitting, we stopped it because we were just running out of time and didn't want to spend more money to train it for longer. But that means that there was still kind of juice to be squeezed. As the quality of the reconstructed images significantly deteriorated, we instead stored checkpoints for the first 8. Which optimize the embedding for 100 steps and the unit for 1,500 steps. Blah, blah. Okay, so they're referring to basically this other technique here called Imagic, this other paper. We selected the final model checkpoint based on the validation accuracy of a classifier trained on the union of augmented samples and subsampled ImageNet. So this is their 10% ImageNet. Union here just basically means they joined both of these, so they have their augmented samples and the 10% ImageNet. They train a classifier on both of those, and then what is the validation accuracy of that classifier, and whatever model has the highest accuracy on the classifier is the one that they use, right? But there's a little bit of a circular kind of reasoning here where if you pick the diffusion model that results in the best validation accuracy for a classifier, it's kind of like, I don't know, it's kind of like you're overfitting in the kind of space of hyperparameters, right? I don't know. For retrieval, we use Leon 5B. This is a dataset here, publicly available dataset of 5 billion image caption pairs extracted via a web crawler. Is this the state of the art? Like, is there something that's better than Leon 5B? That's what I want to know. Like, I feel like Meta probably has that, right? Facebook probably has a better proprietary data set than Leon 5B because they have Facebook images, right? Instagram images. Usually Instagram images and Facebook images, there's a text that you put associated with it. So I feel like Facebook actually has the best data set for a clip model or a clip successor, right? Because they have literally a decade worth of image and text pairs, right? Versus a company like Google, I don't know if they have that data set, right? They just have the web, the internet, and everybody has access to that. And then a company like Microsoft, they don't really have a very good image text data set either, right? So it seems like the best image text data set that is available is probably belongs to Facebook. The clip image embedding was consistent with the caption embeddings. This filtering acts as a weak form of supervision that retains those images where clip is more likely to work. Okay, so they fed the image caption pair, so the image is, of course, an image, and then the caption is text. They feed the caption through clip, they feed the image through clip, and then both of those result in a vector, right, an embedding, which should be in the same shared space, right? Clip's embedding space is both image and text. So if those vectors are close together, then they're going to say, okay, this image caption pair is good. If the vectors are different, then this image caption pair is no good, right? Here we go. Here's the actual performance here. Let's actually wait to see because they're probably going to tell us to look at it in the results. So let's finish this section here. The dataset provides a clip embedding nearest neighbor search index for each instance and an official package clip retrieval allows for fast search and retrieval. We use this to retrieve 130 images per class. Images with a layout aesthetic score less than 5 were discarded to allow a fair comparison with Stable Diffusion 1.4. For a fair comparison to our generative augmentation methods, we use the same safety checker. It's often necessary to retrieve more than the desired number of images, which we do this by increasing the number of nearest neighbors. So 130 nearest neighbors per image. To avoid using the same image multiple times, we apply the duplicate detector of the clip retrieval package. So they keep referring to this. Clip retrieval. Give that a star. MIT license, I like it. Easily compute clip embeddings and build a retrieval system with them. That's pretty good. I wonder what they use for their vector database here. What are they using? Let's look at the requirements. There it is, it's face. So they're using basically the same, we saw this one before, this one here, yeah. Similarity search. This is the Facebook, basically vector DB. Contains an algorithm that searches in sets of vectors of any size. So there's a lot more popular vector DBs now. There's a lot of like fancy startups that are doing it. So, but it seems like everybody's still using Face. FAISS. Facebook AI Similarity Search. In the following section, 4.1, blah 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 blah. Okay. Table 1 corresponds to one section. Okay, so we have table 1. 10% of ImageNet versus 20% of ImageNet. Look at that. Double your data set size, and your accuracy goes from 57 to 50 or to 70. So, you know, it's really showing you that the size of the data set is just better than anything else. If you can get more data, you're going to get a better result, right? There's no amount, look at this, no amount of fancy augmentation beat simply doubling the dataset size, right? So all of these techniques here are based on 10% of ImageNet. So if you have 10% of ImageNet and you have your fancy augmentation techniques with like the clip prompt and like all this crap that they were describing, the best you're going to get is 62%. If you simply double your dataset size and now train on 20% of ImageNet, you're going to get 70% accuracy. So to me, these three numbers tell the entire story right here, is that like all these fancy techniques that they're describing in this paper, at the end of the day, like if you have the ability to find more data, that's what you should be doing. Try to go out, try to find another data set, try to scrape more images, try to collect more images. It just makes, you know, that's kind of really what I was looking for, is that those three numbers right there is 57, 70, 62. It's like disgusting how good it works. But okay, if we look at the different techniques that they have, they're all kind of about the same, right? 60, 60.1, 60.8, 60. These are all basically borderline the same. Right, like the error bars on this are 0.4. So this could be as low as 60.6 and as high as 61.4. So really this isn't that much better than this because the error bars, you see this? The error bars on here are 0.1, so this one actually has a little bit better. Challenges for generative augmentation methods. Before discussing the results, we highlight 4 challenges. Class ambiguity. Some class labels have multiple meaning leading to class ambiguity. For example, generated images of the class papillon. Papillon means butterfly in French. Shows butterflies of the species. However, in ImageNet, this class is a dog. Yeah, so this is a problem, is that in language, right, a lot of words basically mean multiple things. So when you take a word and you turn it into an embedding vector, right, that embedding vector means has within it the semantic meaning of multiple things. So this is a problem with the embeddings that come from text, is that they're not going to have the same, like, there's kind of a little bit of semantic ambiguity there. Yeah, for example, crane can sometimes refer to the bird, or it can refer to a machine. Another challenge is to generate images of sufficient diversity. Most of the considered augmentation methods generate objects in similar styles and semantic settings. For instance, in ImageNet, objects can appear in various semantic styles and image quality, domain shift. Augmentation methods must be flexible enough to adapt to the distribution of images. Okay, I would say that the distributions of images in ImageNet and Leon are probably pretty similar, right? It's not like you're talking about X-ray images and underwater images or something like that. You're talking about RGB images captured from cell phones usually. So I would say the distributions are more similar than different. And finally, fidelity. Generative methods must provide high-quality samples that match the photorealism. Yeah, you don't want to have a distribution of generated images that is very different from the distribution of ImageNet. And this has always been a problem in synthetic data generation, is basically that the synthetic distribution is kind of different from the real distribution, and figuring out ways to do that sim to real, right, synthetically taking that synthetic data set and transferring that data distribution such that it overlaps your real data distribution, that's a really hard problem. To establish the baseline classifier performance, we trained on our 10% ImageNet subset, achieving a top accuracy. Since all augmentation methods double the size of the dataset, we consider an upper bound performance by using a 20% of the original ImageNet. Yeah, I mean, I don't know. To me, this tells the whole story here. 57, 70, 62. Unconditional generation. So Boomerang is another paper that they're kind of comparing to, which sequentially adds Gaussian noise and then uses a diffusion model to denoise elements of the target. So this is the kind of one-step add noise, one-step remove noise, and then you get a slightly different image, and then you train on that. Without altering the diffusion model or prompts, this results in a lower top one accuracy compared to the original subset. Only slightly distorts the original images, leading to an overall decrease in performance. Okay, so you can actually do that. You can create augmentation strategies that actually result in worse performance, which is important to note, right? Not everything you do when you're trying to figure out the best hyperparameters and the best techniques and the best augmentation processes to use in your kind of machine learning problem, not everything you do is actually going to make it better. You can spend like 2 weeks implementing some new regularization loss or like some new like cool little trick, and then only find afterwards that it makes your stuff worse. And that sucks, you know, like that's one of the worst things that can happen to you when you're doing machine learning, where you spend all this time implementing a new little thing, new little widget, you put it on your technique, and then it actually does worse. Summary. Using diffusion models off the shelf without adaptation or conditioning using the target dataset is not beneficial and can even deteriorate the class performance. So here's ImageNet, right, and then here's Boomerang, and then here's the difference. Sorry, again, I go to this GitHub link page, show 404. So type in Unreal Engine Quest 2. And then go here. Type Unreal Engine Quest to GitHub. This is what you want. And specifically, you want the samples, right? Oculus samples are examples, right? So you see here, these are starter scenes. So starter scenes for Unity with hands, starter scenes for Unity for movements, and depending on what you want, Olsey, you're going to want a different Unreal here. So you could basically start from here. This is Unreal Hand, so this is hand example. This is going to be an Unreal Engine kind of like game that you can start from that has all the meta quest stuff in it. So search for this, search for GitHub Oculus samples. Okay, so back to here, we have our ImageNet, we have our boomerang, and we have our difference. So this is basically the diffusion model that adds one step of noise and then uses a diffusion model to remove the one step of noise, and then you can see the difference between them. So to humans, these images largely look exactly the same, but there is a slight difference. Prompt conditioning of the diffusion model. One way to adapt diffusion models to the target data set is via conditioning mechanisms that guide the image generation, right? So this is where you put in your word embeddings in order to get a image generation that is conditioned on that specific word embedding. So you give it dog, it generates a picture of a dog. Simple prompt is basically just you have your dog or cat or tiger shark or whatever, and then you're basically just adding this prompt engineered kind of like boilerplate, which is just a photo of and then the thing. This improved over the 10% ImageNet baseline to a top one classification accuracy of 60. Tackling class ambiguity by white space removal. While generally mitigating class ambiguity is a hard problem, we focus on ambiguity introduced by class names composed of multiple words. To this end, we investigated the variant simple prompt, no white space, remove the white space from the class name. What? That works? Overall resulted in slightly degraded performance. Okay, yeah, I don't know. This is a weird idea where you just combine the words, like remove the white space and somehow it does better. Like, I don't know, that seems stupid. To increase the diversity of the samples, we made use of multiple prompt templates. We use clip prompts, which randomly selects one of the text templates by clip and increases classification accuracy. But I mean, these numbers are so tiny, like the performance increases and decreases are so small that I don't think you can like make conclusions from these. Images with texture-like contents. Surprisingly, these slightly more elaborate templates, just adding a few more words compared to simple prompt, improved class ambiguity in some cases. Summary. Augmenting a dataset with images sampled by prompt-based conditioning techniques improves the downstream classifier performance, but various challenges remain. ImageNet is more than a decade old, and some images are older and of a different style. Generated images do not match the domain because they are too artificial, sometimes even like a computer rendering. This tendency has been amplified being trained on a subset of Layon, which was filtered to contain only aesthetic images. Ah, okay. So there's a subset of Layon for only aesthetically pleasing images. Found that adapting the diffusion model by only editing the prompt offers limited improvement when used for augmentation. Explores a more advanced set of methods that additionally tune parts of the diffusion model to personalize it. Yeah, so they're basically going to fine-tune Stable Diffusion specifically to the small ImageNet that they're using, and then hopefully it'll perform better. But I don't like this technique. I feel like this is like too much overfitting, right? The general diffusion model architecture has multiple components that can be fine-tuned. We start by fine-tuning one conditioning vector per class to optimize the reconstructing object. So not only are they fine-tuning on the small ImageNet, but they're fine-tuning specifically the conditioning vector per class. So that is just so much overfitting. Achieves an augmentation which is on par. Okay, so here you have different generated images. What do we got? Example images, a 10% ImageNet. So here are the original ImageNet images. Images generated by our prompt-based sampling. Images to the prompt, a bad photo. Black and white photo, cartoon photo. Yeah, so kind of like a style transfer here where you can see they have. So this is the original images of beer. This is all the different techniques that they use, and then you can see this. The reason they show you this papillon here is because I think this dog breed is called a papillon dog. So you can see how it's kind of confusing because sometimes you get butterflies, sometimes you get the dog. Scooter here, mostly you get the actual like kind of Vespa scooter, but sometimes you get the like scooters that you would see in an American city, like the bird scooters. I feel like the beer glasses are pretty consistent. And then the desktop computer, this is what they were referring to, is that ImageNet is so old at this point that the computer like looks outdated. This is like a Windows 95 computer, you know. Fine-tuning clusters of conditioning vectors. Using a single conditioning vector for all images from one class might be insufficient. We explore fine-tune cluster conditioning. We generate k clusters of images per class before fitting a conditioning vector to each individual cluster. So this is the kind of averaging thing. Find that using k equals 5 clusters slightly improves the accuracy by 0.1 percentage points over using k equals 1. Performance decrease. So I don't know, if you're not getting good performance with k equals 1, you're not getting good performance with k equals 10 and 15, but you're getting good performance with k equals 5, and your quote-unquote good performance is just a 0.1% improvement, I think what this means is that it's largely not doing anything, you know? It's too much noise, like the error bars on this are too big, right? Like 60.8 with plus 0.2 performance error bars is basically like you can't compare that to 60.6 with 0.3 error bars. It's not statistically significant, right, as medical people would say. This method learns a pseudo word representing the class concept combined with the randomly drawn textual description of the generated image. This method improves the photorealism according to humans, right? But we don't know how neural networks really care about that photorealism. That's still kind of not understood. And then fine-tuning the denoising. So we explore fine-tuning the denoising module jointly with the conditioning vector. So all of this page here has just been slightly different ways of fine-tuning. So fine-tuning just the conditioning vectors, using a kind of cluster of the conditioning vectors, fine-tuning the diffusion model, specifically the model part or just the denoising part, but I don't know. I still feel like this is all kind of the same, where it's like the error bars are just too big to have any meaningful result. Summary, personalizing diffusion models improves in the matching domain, better improve upon prompt-based techniques to reduce class ambiguity. Suggests that we can leverage, I don't know, maybe not. To me, it's telling me it's not really doing much. Retrieving from the pre-trained data. We showed that diffusion models are helpful for creating augmentation data. However, it is unclear how much value the DM's generative capabilities add compared to simply using their pre-training data directly for augmentation. To answer this question, we propose a simple retrieval method for fetching images from the DM's pre-training data that are semantically closest to the simple prompt. Yeah, so if the diffusion model is just a compressed form of the distribution of data that it was trained on, right, in this case Leon 5B, then can't you just use Leon 5B images in your training technique and then get the same result? And that's what they're saying here. Augmenting with this data outperformed all investigated diffusion model-based approaches. So that's the nail in the coffin. You know, I've been kind of shitting on them a little bit here, but that's the nail on the coffin, is that just using retrieval, which is basically just saying, hey, no diffusion model, none of that nonsense, no fine-tuning diffusion models, no prompt engineering, none of that. All we're going to do is just take images from Leon 5B and use those. And you get better performance than any of these other ones here. So, I don't know. I like these kind of papers because they tell you what not to do, right? Yeah, exactly. So much buzz about generative augmentation, whereas dudes just find more data via similarity search. Yeah, and it's what I'm saying. And this is kind of why I like these papers, because sometimes papers try really hard to convince you that their novel technique is somehow revolutionary because, right, they need it, right? As a researcher, you're not going to publish that many papers, so you want every single paper to be big. You want it to get viral. But sometimes you publish a paper and the results are bad, right? Where it's like, hey, I tried a bunch of things and none of them worked. And this is one of those papers where they're like, hey, we tried to use diffusion models to see if we could do data augmentation, and it turns out that none of the different techniques that we tried could work, and just using them to retrieve a bunch of images from a Leon 5B dataset and then fine-tuning and then basically just using those in our dataset worked better. And you know what worked even better than that? Just using twice as many images. So I like this paper because it confirms kind of my intuition that if you have like 10 points to spend in your little talent tree, if you have like a week or two of time, use that week or two of time to find more images, increase your data set. Don't try to implement some fancy diffusion-based data augmentation. Just literally find more images to train on, and that'll improve your performance better. So I think it's good. I think this paper teaches you something, even if the results themselves are not necessarily the best. When does augmentation help? To better understand the failure cases, we check for each class if augmentation method is beneficial. To this end, for each class, we compute the performance improvement of the downstream class bar using the augmentation method compared to only using the original ImageNet samples. There are still many classes with their performance decrease up to 10%. Yeah, so not only is the performance not improving, but actually for some of the classes it decreases, so it's actually more sinister than that. So worst deterioration, best improvement. So the best, let's zoom in here. The best improvement for this type of data augmentation came for these, right, which looks like pictures of scorpions and sheep and maybe like whatever this is, a chest. The worst improvement, right, was cats, dogs, horses. So it seems like the classes where you have a bunch of data for ImageNet actually got worse with this data augmentation technique. And then the classes where you don't have a bunch of data, so these kind of less represented classes like scorpion and salamander, those are going to be the ones that you're going to perform better on, which kind of makes sense because the less images you have of a specific category, the better you're going to benefit by having any data augmentation technique. But if you already have a bunch of images of that category, the data augmentation technique might actually be worse. Does that mean that diffusion models have really low recall on some of the classes, like they just don't cover the distribution very well and simply generate similar images? Yeah, so any kind of model, right, any kind of neural network like a diffusion model is going to is basically trying to create this embedding space, right? It's trying to create this embedding space. And if 80% of your data set is dogs, right, then it's going to, over time, use much more of its model capacity, right? It's going to spend a bunch of time making sure that that embedding space is very good in the area where the dogs are, right? So it's like most of its energy, most of its like embedding space is going to be focused on that dog class. But if you have classes that have very low representation, like, I don't know, like salamander, maybe there's only 2 salamander images. So at that point, the embedding space is not going to be very good for salamanders at all. And there's probably a similar type of thing with diffusion models, where diffusion models are going to be very good at certain types of things that come up over and over and over and over again in the Leon 5B dataset. Maybe people, I don't know, like dogs, things like that. But the diffusion model is going to be really bad at things that are not within the data distribution, right? At the end of the day, the diffusion model is just a compressed representation of the dataset. And any bias in that dataset, any dataset bias that you have is going to be reflected in the diffusion model. So, yeah. Yeah, exactly. So, I don't know. It all just comes down to the data. Like, at the end of the day, all of these neural networks, like, they can't, if your data is shit, the neural network is going to be shit. Like, you can't make the neural network better if your data set is shit. So really, don't spend your time trying to optimize all these hyperparameters and model architecture things. Like, just focus on making that data set as balanced and clean and low biased, well represented across all the different classes and so on. Garbage in, garbage out. Yeah, that's another way of saying it. And you know, people don't like to hear that, right? Because a lot of people, they go into machine learning engineering and machine learning research, and they want to use the math, right? They want to think about new techniques, and it's so much more fun to come up with a new type of transformer variant than it is to sit there and clean a data set. But unfortunately, the more and more and more you kind of like work in this space, the more you realize that cleaning the data set is by far the most kind of bang for the buck thing you can do. And it sucks, right? It sucks that you went through all this school and all this math and you learned all these interesting things only to then spend your time sitting there cleaning some X-ray data set. But unfortunately, that's kind of just the way it works. We have evaluated multiple methods to prompt and personalize diffusion models and their usefulness for data augmentation, showing that none of them beat the simple baseline of retrieving images from the diffusion model's pre-training dataset. Why is the retrieval baseline so hard to beat? One reason might be that the retrieval potentially accesses more information, as the pre-training dataset is usually much larger than the weights of the generative model trained on it. So they're basically saying, hey, the compressed form of the dataset in the diffusion model is not as good as the full, raw, unadulterated dataset. It's still unclear that if the generative model captures all the relevant information. However, diffusion models could possibly improve upon the so far superior retrieval by generating a large number of additional data and more diverse and compositionally novel images. Generating out-of-domain samples, a photograph of an astronaut riding a horse. Yeah, I mean, out-of-distribution generation is kind of one of the bigger selling points of synthetic data approaches. We showed that personalization methods are a good step in this direction. However, they typically focus only on creating variants of specific given images. To unlock the true potential of diffusion models for generative augmentation, new methods that capture the target dataset manifold as a whole are needed. So we need better ways of compressing dataset distributions into a manifold that contains all the semantic knowledge. Limitations. We only consider the setting. Yeah, of course, they're only doing this on ImageNet and with a very small ResNet. So it's kind of like in medical papers, right? They do it on a mouse, right? And it's great because mice live faster. They like kind of live and die faster, so you can like see the full life cycle of the mouse much quicker. So you can do science faster. And using a ResNet 50 is kind of the same concept. It's like, hey, let's try out these strategies on these very small models so we can basically do them quicker and try more combinations. But at the very end, when you get your results, you have to then put the caveat of like, hey, this was only tested on mice, or like, hey, all this stuff that we found only applies to ResNet 50s and ImageNet. So maybe the same experiment, if you did it with a much bigger model and you trained with a better stable diffusion, maybe it works a little bit better. So still to be determined. Diffusion models are a very active research area, and new methods and applications are published on a daily basis. Hence, our experiments could only capture a subset of possible methods. It would be interesting to explore the scaling behavior for our higher augmentation ratios and the scaling behavior for larger classifier models and larger just data sets in general. Conclusion. We have shown that simple retrieval baseline can outperform a wide range of diffusion models-based augmentations. Given the fast rate of progress, it is not possible to definitively say that retrieval cannot be beaten, and we believe that diffusion models have the potential to improve. Nonetheless, the strength of the retrieval performance makes it clear that future works using diffusion models for augmentation should also compare against this baseline. Cool. Is there anything interesting here? Just more images. Alrighty. It was a nice little paper, you know? Interesting stuff. I thought it might actually give you good performance. I thought that data augmentation with diffusion models was a cool idea. I'm glad that they were able to admit that it doesn't work very well, but you know, I think we learned something by reading this, and our intuition is a little bit better, and we understand that, you know, data is king, and if you have more data, you should definitely do that instead of focusing on data augmentation. But overall, an interesting little paper. Hope this was useful. Thanks for listening. Tomorrow we're going to be looking at LangChain. So LangChain is a large language model application kind of framework by Max F. Berg. Yeah, did you guys know this guy? Max F. Berg? I don't know who that is. I've heard this guy before, Francesco Locatello. But yeah, tune in tomorrow for LangChain if you guys want that. If not, have a great day, have a productive day, and see you guys tomorrow. Can you post the file in Discord, please, dude? Dude, Olsey, you need to learn how to search the internet, man. I don't know what's the issue. Yeah, thank you guys. See everybody later.